Welcome to LLMs for Executives and Dummies series. Today we will cover overview of LLMs. So here we go. Okay, let's start with asking the question, what is a language model? The classic definition of a language model is a probability distribution over a sequence of tokens. The probability intuitively tells us how good a sequence of tokens is. For example, if the vocabulary is 8 ball cheese mouse tea, the language model might assign probability for the mouse ate the cheese as 0.02, probability for the cheese ate the mouse as 0.01, probability for mouse the cheese ate as 0.0001. The language model should assign mouse the cheese ate a very low probability implicitly because it's ungrammatical, that is syntactic knowledge. The language model should assign the mouse ate the cheese as the highest probability than the cheese ate the mouse, implicitly because of world knowledge. Both sentences are the same syntactically, but they differ in semantic plausibility. Now, here are some of the key attributes of a language model. A language model is a probability distribution P over a set of tokens. Intuitively, a language model should have linguistic capabilities and world knowledge. An autoregressive language model allows for efficient generation of a completion given a prompt. The temperature can be used to control the amount of variability in generation. For example, if t is equal to 0, deterministically choose the most probable token x at each position p. If t is equal to 1, sample normally from the pure language model. And if t is equal to infinity, that means sample from a uniform distribution over the entire vocabulary. So here is a language model summary that you can keep in mind. Language models were first studied in the context of information theory and can be used to estimate the entropy of English. N-gram models are extremely computationally efficient and statistically inefficient. N-gram models are used for short context lengths in conjunction with another model, that is acoustic model for speech recognition or translation model for machine translation. Neural language models are statistically efficient but computationally inefficient. Over time, training large neural networks has become feasible enough that neural language models have become the dominant paradigm. So now let's ask the question, what is a large language model? The obvious answer is increase in size. Now, what do we mean by large? With the rise of deep learning in the 2010s, the major hardware advances like GPUs, the size of neural language models has skyrocketed. The following table shows the model sizes have increased by an order of 5000x over the last 4 years. And here's the table. As you can see, in Feb 2018, Elmo was trained on a parameter of 94 million. And then at the bottom, we have Gopher from DeepMind in December 2021, which has the number of parameters as 280 billion. That's huge. Now, continuing on the large language models, let's talk about emergence. What difference does scale make? Even though much of the technical machinery is the same, the surprising thing is that just scaling up these models produces a new emergent behavior, leading to qualitatively different capabilities than qualitatively different societal impact. Now, what are these capabilities? Whereas language models up till 2018 were mainly used as one component of a larger system, for example, speech recognition or machine translation, language models are increasingly becoming more capable of being a standalone system, something that would be unthinkable in the past. We call that language models are capable of conditional generation. Given a prompt, generate a completion. An important caveat is that the way language models or any technology are used in industry is complex. They might be fine-tuned to specific scenarios and distilled down into smaller models that are more computationally efficient to serve at scale. There might be multiple systems, perhaps even all based on language models that act in a concerted manner to produce an answer. Let's briefly talk about the risks. So, first risk is reliability. If you play around with GPT, it works better than you might expect, but most of the time, but it still fails to produce the correct answer. Worse, the answer can seem correct and there is no way of knowing. Social bias. It has been well documented that machine learning systems exhibit bias. They have performance disparities across demographic groups. but their predictions can enforce stereotypes. For example, we can probe the biases inherent in a language model by looking at the probabilities of pairs of sentences that differ only by one pronoun. Toxicity. Large language models are trained on a huge amount of internet data, which inevitably contains offensive content. Real toxicity prompts is a dataset that evaluates a language model's propensity for producing toxic content, disinformation. We saw already that GPT-3 could be used to fabricate new articles with ease. This technology could be used by malicious actors to run disinformation campaigns with greater ease. Because of large language models' linguistic capabilities, foreign state actors could much more easily create fluent, persuasive text without the risk of hiring native speakers. Security. Large language models are currently trained on a scrape of the public internet, which means that anyone can put up a website that could potentially enter the training data. From a security point of view, this is a huge security hole because an attacker can perform a data processing attack. Legal considerations. Language models are trained on copyrighted data. Is this protected by fair use? Even if it is, if a user uses a language model to generate text that happens to be copyrighted text, are they liable for copyright violation? Cost and environmental impact. Finally, large language models can be quite expensive to work with. Training often requires parallelizing over thousands of GPUs. For example, GPT-3 is estimated to cost around 5 million, and this is a one-time cost. Inference on a trained model to make predictions also imposes costs, and this is a continual cost. So here's the overall summary for large language models. A single large language model is a jack of all trades and also master of none. It can perform a wide range of tasks and is capable of emergent behavior such as in-context learning. They are widely deployed in the real-world systems. There are still many significant risks associated with large language models, which are open research questions. Costs are a huge barrier for having broad access.